Thank you, Leandro, for the nice introduction. Thank you, Luigi, for the nice invitation. And it's great to be here. It's my first time here. Okay, so today I'm going to talk. My main interest nowadays is quantum thermodynamics, but I also heard that here there is maybe some interesting in quantum computing. So I've tried to have a talk on thermodynamics, but then I'll try to catch also on quantum computing as well. Okay, so thermodynamics is, as you probably know, is the science of engines and refrigerators and heat pumps. But of course, you may also want to reduce the size of these engines. And as physicists, we like to explore the fundamental limits in how we can miniaturize objects. And here you see, for example, this I think is the smallest steam engine with a Guinness record. And then this is the molecular engine or motor. And this is a quantum dot single electron engine. Okay, this, again, you probably know, if you have a petrol car, you know how combustion engines work. This is an example. So this is the so-called Otto cycle. I don't know if we can, that's what you're trying to do. Okay, and the Otto engine works with two isochoric in the PV diagram. This is two constant volume transformations, cooling and heating, and two adiabatic expansions. And no, can you click now back on the, yeah, cool. And now you can, sorry, and I didn't say if you want to interrupt and ask questions or make a comment, please do. And then we can ask, okay, can we actually do the same cycle, but rather than with an ensemble of particles like in a gas chamber, can we do it with a single particle? And this is like a cartoon, a picture of a single particle doing an Otto cycle in a harmonic potential. The particle can be classical or quantum. So this green blob that you see can be the probability distribution for a quantum particle or the probability distribution for a classical particle. So it doesn't have to be necessarily quantum, okay? And here you see again the cycle, but this time we see the harmonic potential. The compression stage or stroke is done by increasing the frequency of the harmonic trap. Then you need to couple the system to some heat buffs in equilibrium and increase the temperature. Then the expansion means we release the trap, so we lower the frequency of the trap, and then we cool down and we close the cycle. So we couple it again to a thermal bus in equilibrium. And this was actually realized experimentally in the group of Ferney and Schmidt-Kahler in trapped ions. So this is a Paul trap, which is capable of trapping charged particles, so ions, in the center of this trap. Normally, Paul traps, they have the 4 electrodes parallel to each other. But here what they did, they put the electrodes with an angle so that the transverse frequency here is much stronger than the transverse frequency here. So the idea is that when the engine starts to work, the particle is kind of shuttled back and forth between two positions where the transverse frequency is different. So this is going to be the compression expansion. And the particle is subject also to laser cooling with two different lasers at different detunings. So the original proposal was to have a blue detuned laser, which was the heating of the particle because it will increase its energy, and a red detuned laser that was going to cool the ion. In reality, in the actual experiment, so the proposal was this PRL 2012, and the experiment was 4 years later. In reality, in the experiment, they removed the blue detuned laser because the ion was heating up naturally by the noise of the electrodes and so on. So they were only putting the cooling, and they were putting at periodic intervals. Okay, so they didn't have this. Okay, so this was the first single atom engine doing the Otto cycle. From the point of view of the motion of the ion, this is all classical. Mostly is classical because the motion can be well described by Newton's equations. Okay, it's only the internal state of the ion, so the electron, if you want, that is quantum, and this is allows for the Doppler cooling. Yes, it's super small, super small, the efficiency. Yeah. So they compute it, but
make a kind of
Yeah, they can compute they can compute the work and the heat. Yes, and the efficiency, if I remember, is like a few percent of the Carnot engine, of the Carnot efficiency. Good question. Good question. So I told you about the transverse field, but there is also a longitudinal field. And the particle, when it's going in this direction, is going downhill. And when it's going in that direction, it's going uphill. So when the electron is going uphill, it's doing work against the electric field. And if you want that work against the electric field, could in principle be used to charge a battery. This is not done in experiments, but in principle, if you could connect a battery somewhere, that's the work. Is the piston. The piston is the longitudinal motion of the ion. Yeah. Any other question? Okay. Okay. So other. Yep.
So when you say why? Because you might imagine it's a very clean system, right? And I would have guessed, oh, hey, it gets pretty close to the efficiency of that.
No, because there is a lot of micromotion. I'm a theoretician, okay? So take it with a grain of salt, but there is a lot of micromotion of the ion. So it's not true that it's moving only along the axis, but the particle is, jiggling around in the trap, and there's a lot of micromotion.
It's kind of a driven motion, right? Like it's driven from the trap.
Yeah, but it's noisy. But it's noisy. It's not controlled, the micromotion.
But it's kind of a classic drive. I think it's not really might lead to heat effect.
Yeah, but it's not the controlled. I'm not, again, sorry that I'm a theoretician. It's not controlled, so it's deterministic if you want, but it's almost like chaotic because this is the motion of the ion in the Seldol potential, no? In the Paul trap, so there is a RF field which is rotating, and the ion is kind of moving almost randomly or chaotically in this potential, and this is detrimental to the motion itself, because what I show you was the ideal case is that the ion only moves along the axis of the trap, but in reality it's not. It's moving away from the center. Yeah. This is my understanding of why this is so bad.
And this then leads to somehow wasting some energy.
Yeah. It's additional heating that is wasted, so the work is not produced as efficiently. Okay. Other examples, maybe a little bit more quantum. So that was really classical. Other more quantum engines. These are this is an experiment in NMR with a single spin as the engine. I think, yeah. So this is a nuclear spin of a carbon atom, which makes the work, and then the environment is simulated by the nuclear spin of a hydrogen atom. So, okay, so there are the different stages are here. There is expansion and compression, and then the coupling is the coupling between environment, the hot and the cold environment. This is truly quantum because if you want, the two qubits are genuinely quantum particles. They behave quantum mechanically. Another one, if you want, is more of a demonstration, or I don't know if you want to call it experiment or whatever. So these people, they took the IBM quantum computer. They programmed a bunch of gates. I will talk maybe later about this more. And they simulated an engine where they have, again, a hot bus, a cold bus, and two qubits as the working fluid of the system. So they do controlled collisions between each qubit and its bus, and then between the two qubits of the system. So these are the two more quantum experiments that are there nowadays.
Wasn't the minimum Turing machine made with 3 ions?
With three ions, yes, it's true. So this was the Singapore ones from CQT, sorry. And
the experiment was there, but the ideas were
the experiment was there, and again, this is classical, right? This is quantum, but it's the emotional degrees of freedom of the three ions, no? So it's the three normal modes of the ions. So this is in the transverse directions of the right. Okay. So I thought that that was also in the classical regime. So the internal states of the ions, fine, it's all quantum. I thought that the emotional state was classical, but I may be wrong. And then there are a number of proposals for atomic engines with cold trapped ions, sorry, with cold atoms. And this was one of the first proposals with two species bosonic atoms, where one of the atoms make the environment, the other atom is the working fluid, and then there are other in condensates, other proposals in condensate. The newest experiments in cold atoms, one was more a transport, not really an engine, but more a thermoelectric process where atoms go from the hot environment to a cold environment through a constriction. This was in Tillman-Essinger's group. And there are two more recent experiments in the group of Arthur Videra, one with theoretical support from Eric Lutz, the other one from Thomas Busch. And this one was with an impurity in ensemble of atoms in a BC, and this one was going from the BCS to BC crossover to do the transition in the engine. So this is a little bit of the experimental work so far. Quantum thermodynamics, more broadly, is an area where we study out of equilibrium. So compared to the traditional setting that you study in textbooks, this is the setting where the number of particles may be small, and you are not always in equilibrium. And because the number of particles is very small, the fundamental laws of thermodynamics work only on average and not, so they have a lot of fluctuations. It's dominated by fluctuations that could be quantum or classical. And so one of the things that are studied are how the laws of thermodynamics emerge when you have a small number of particles and when you are out of equilibrium. And so there are modifications. We will maybe see one of these modifications later. I come a little bit more from the quantum information side, where it has been investigated how quantum correlations, for instance, entanglement, can help enhance the functioning of engines. There is a more maybe abstract or theoretical framework, which is called resource theory of thermodynamics, where people ask themselves how the fundamental laws of thermodynamics can be inferred from this framework. Of course, applications in quantum technologies, and very recently there's been this quantum energetic initiative where people are asking, so are putting thermodynamics in context with quantum computing in a different way, in the sense of how much energy quantum computers waste. So not how to produce a quantum engine or a refrigerator, but rather, okay, I have this quantum computer. I know that it has a quantum advantage computationally, so it's the fastest computer compared to classical computers. But how much energy do they consume? And maybe a more ambitious question is, given a quantum computer, can it have an advantage energetically? Can it compute things more efficiently in terms of energy consumption compared to a classical computer? This is still really maybe at the beginning, okay, of this exploration. So other maybe branches of quantum thermodynamics is thermalization. So if you have a system that is closed in a pure state, imagine a many-body system, you give it a kick or something, and you want to know, will it thermalize by itself? Okay, so this is thermalization of closed pure systems. And if it does thermalize, then can you define a temperature? Can you measure the temperature, so the context of thermometry? And what is the ultimate limit in the precision with which the temperature can be measured? So these has connection with phase estimation and so on, parameter estimation and so on. maybe in parallel to this, there's also people looking at heat transport and thermoelectricity. So this is when electricity is generated by a temperature difference or when heat current is generated by an electric voltage or bias. So this is a little bit, in my view, the current panorama of thermodynamics. Okay, in what remains of the talk, I split the talk in two parts. I don't know if I'll manage to get to the second part, but I'm happy, you know, later in a coffee or something, we can talk about the second part. In the first part, I'll tell you how we can use quantum computers to simulate quantum thermodynamics, in particular open quantum systems and thermodynamic processes. The second part instead is the other way around, in the synergy between thermodynamics and quantum computing, is to be inspired by thermodynamics to speed up certain quantum optimization tasks, in particular in connection to annealing. Okay, so let's go to the first part. So that's the outline motivation. I'm going to talk about collision models, and I'm going to talk about engines with quantum coherent bus, and the second part is accelerating quantum annealing with collision models. Okay, so first part, open quantum systems, maybe the theoreticians among you use them daily for describing transport, complex systems, quantum technologies, of course, and thermodynamics. Usually the approach that we use is to take a microscopic model. So this could be, for instance, the Caldera-Leggett model or spin boson model, or if you want, you can have fermionic bus or more exotic things depending on your setup. A spin star or spin network can be more appropriate in, for example, in solid state with impurities. And in this setup, the system is permanently coupled to a bus, to an environment. In this case, this is represented by harmonic oscillators, but it doesn't have to be. And normally, this is in equilibrium environment. So that's the microscopic model. Then we cannot solve it because it's a many-body problem. And we do a series of approximations, and typically we do the Born-Markov approximation, and we end up with a nice master equation for the system. So that's fine, but sometimes when the system is very large, this lambda approach may be complicated. So an alternative is provided by these collision models. Some other people call it repeated interaction models, where the environment is replaced by a series of units or ancillas that interact sequentially with the system, and they interact for a small time and then they are discarded. In the simplest case, these units are created in equilibrium at some temperature T from an oven, from an environment, and they can be qubits, they can be harmonic oscillator, can be whatever you want. And the evolution of the system will then change depending on what you use here. There are a few reviews already recently, and in this paper we were talking about the thermodynamics of these systems. So what can you simulate with collision models? So if you give me a lambda master equation, can be local or global. So this is a little bit technical. Local is when the system interacts locally with the system, in the sense that the jump operators are local operators, just for example, spin up, spin down, okay? And global instead is when there are global properties, collective properties of the system that interact with the environment. So it can be both, the environment can be thermal or out of equilibrium. So if I prepare my ancillas in a state with coherence, I will produce some more exotic evolution rather than the usual thermal equilibrium master equation. Interactions can be individual or multipartite with the environment, and it can be Markovian, or there are some models, some non-Markovian models that we can also simulate. So all these we can simulate. And what we did in this paper was, given any of these, we can write what we call a multipartite collision models that consists in several buffs that are this is the system, and then there are the several buffs that are shooting these ancilla, these auxiliary systems, to interact with the system with a local interaction or with a more multipartite interaction. After this, in the multipartite collision, we can write a quantum circuit that produces this evolution, and then we can bring this to the lab and hopefully implement it in a real quantum computer. There have been a couple of experiments, as far as I know, of this. One in photonic systems where the collisions between the system and the environment is done just by a normal beam splitter. And here, I think only 1 or 2 collisions where this group was able to do only a couple of collisions, not many collisions. And the other experiments that I know of has been done again in IBM-Q in 2 papers, where you can see, if I remember correctly, this is the system. I'm not so sure. One of these is the system, and then they start to do all the collisions. The problem with the superconducting circuits is that if you want the different ancillas to interact with the system, then you need to do a lot of swap gates to bring the ancilla close to the system. So in the limitation in superconducting computers is the fact that you have 2 ways of producing this. One way is that you prepare all your ancillas in advance, which means that you need to have a lot of quantum computer with a lot of capacity of qubits, and do this swapping, so to get the last ancilla to interact with the system. So that's one way, and of course, it has a lot of limitations. The other thing that you can do instead is that you can, if it's possible to do it, you can reset all the ancillas every time. So you do the collision, and then you reset the state of the ancilla to a thermal state, which again, as far as I understand, I'm not a specialist in this, but as far as I understand, this is a complicated step in the cloud computers. So quantum gates are fast and more or less reliable, while this resetting, re-preparation of the ancilla in a thermal state is very slow and not very efficient. Or yeah. Okay, so far, questions?
So, correctly, but you can reproduce all the standards.
Exactly. Yeah, exactly. I can reproduce any master equation. Okay, I have to say properly. Any Limblad Markovian master equation, and certain classes on non-Markovianity. So I'm going to speak later about non-Markovianity.
Yeah. When you make this collision, so this interaction between your system and the environment, so what kind of system you have in the environment that time after time get in contact with the system? So is it a one-body operator interacting?
Can be both, right?
More complicated in the structure.
Okay, so the simplest case is that it's a simple C0, or it's a simple exchange interaction between 2 spins, okay? The simplest case is that these 2 spins get in the collision, and they do a partial swap or an exchange interaction, okay? That's the simplest. But we consider the case of the general thing where the ancilla, the qubit that is coming, is interacting with a collective transition between 2 states of the system. These 2 states can be, for example, eigenstates of the Hamiltonian that are they differ collectively. Okay, so if you, this I'm a theoretician, and therefore for me, I can always write this. Then, of course, in the experiment, one needs to be able to implement this.
But anytime the environment, you have like one.
If you want, this is the simplest case, but you can consider D-level systems in the environment as well. Yes, and there might be, again, this is the simplest case. You can imagine what you want, but the simplest case is 1. And in the simplest case, they are all identically prepared. But you can also think of situations where you prepare them randomly, and you have additional noise in the master equation. You can do a stochastic master equation if you prepare them randomly. So there are many variations, okay? So it's very flexible. As a theoretical construct, is very flexible, but perhaps even technologically, this could be also interesting.
The goal here, so you propose a new model of decoherence, so to say, right? It's conditional model, right?
Of implementing a decoherence model.
I see. So this is for implementing like linear equations.
Exactly. It's a different perspective, no? So I'm not proposing a new physical model. but I'm proposing how to simulate any master equation, the Lindblad master equation, well-behaved master equation that you can have. And this, I won't discuss in detail, can be done polynomially with the number of qubits in the system and polynomially in time of the simulations that I want to do. So I want to simulate a master equation in time. This is polynomial in time, polynomial in size, and polynomial in error.
So where this works, like,
yeah.
It's right. So, but the difference here is that you have this collision. So these systems are flying by, or how could you?
This is like Soller's papers,
so,
for instance,
so
daily, Andrew daily. Yeah. Yes. Right. In those papers, they assume a master equation, and they assume certain jump operators between, well, affecting the system. This is a recipe to implement that master equation. That's exactly the point.
What is the figure of error that you compare experiment?
Yes, for example, the fidelity of the process. Yes, for instance. For instance, yes.
How do you fix the gates? I mean, because the Lindblad are generic operators.
Yes.
So, Li, how does it translate?
Sorry, say it again.
The operators Li in the Lindblad, how do you map that?
Yes, let me see if I have the slide that I skipped. No, how do I unskip one? No, like this, sorry. Okay. Okay, so that was the one that I skipped, but then, okay. Okay, so suppose this is the most, sorry, this is very, very technical, but I hope you will address like this. So, so this is the most general master equation I can have with Kosakowski, thanks, with a Kosakowski matrix, gamma p, and p depends on all these indices, okay? And it's non-diagonal, so it can be whatever you want. And then this is the interaction between the ancilla p, that has all these four indices, and where the f operators are there, and sigma plus for that ancilla. So this is how it translates. This is still at the level of the collision model.
But sorry, who's the system and who's the ancilla here?
The system is 1 and 2. My collaborator decided to do it like this. In this case, because it's the most general thing you can have. Yes. So F is an operator in the system. Your system can be 50 qubits, and F is an operator on the 50 qubits. Then whether this is easy to implement, this is not the question. Sorry. And then as long as you make this interaction, this transition coupled with the sigma plus, with the spin flip of the ancilla, then it's fine. Okay. So then you, yes, then you concatenate all these gates. All these gates are the evolution with this interaction Hamiltonian. Okay. And then we demonstrate, if you do this for delta t going to 0, you get this master equation. Then the next step, is to translate this into a circuit. Okay, and then you need, I don't know, compilation, et cetera, et cetera. You need some quantum software to do it. Yes, Luigi.
Just to be sure, so you are saying that, okay, I start from a master equation, and I know the Lindblad operator.
Yes.
Okay, so I can, in full generality, you are saying, look, I construct an interaction between one Lindblad operator and one.
Each Lindblad operator needs to be coupled.
All the time? Or
all the time.
So this is a general.
Yes, all the time for all the operators there, for all P. And P is the different things. So here, yeah, because we had the two indices on the left and on the right. So this is the non-diagonal thing. I think alpha was the bus and M was the operator in the system, okay? So this is why this is so general. It's not easy, okay? For a complicated system, it's not easy, but this gives you a recipe to do it. If you have a single qubit in the system, then it's, of course, you couple sigma x of the system with sigma x in the ancilla. But if you have a more complicated system, you can still do it. Yeah.
So as I understand now, it's kind of as you just described, a very general model to simulate any master equation. How does this now connect to this grand theme of thermodynamics? So
this is coming. This is coming. This is coming. Hopefully, this is coming. Yeah, yeah.
But the state doesn't understand that. So I'm confused that you can do it with a single ancilla, because typically the Dirichlet equation would emerge because you're ignoring the entanglement with the very massive environment, many particles, and therefore it's strong correlated, very strongly correlated. Whereas here it's a single one. So
for each term in the master equation. It's a single ancilla for each P, for each M alpha. No, it's not easy. It's not that magical.
Yeah.
Thanks.
Yeah. Well, my concern was that typically, if I interact with, complicated model of harmonic oscillators or any of those models, your entropy is large.
Mm-hmm. The system entropy. Yeah.
Tangled.
Yeah, yeah.
But if the ancilla is a single particle, it's limited to a unit of entropy.
No, but at each delta t, one new ancilla comes.
I understand.
And so the environment is gonna.
You are putting the same ancilla.
No. I have to do the. No. I have to refresh the ancilla and send another one identically prepared. Yeah. So if you want to generate the continuous master equation, delta t has to be small compared to the time dynamics of the system, of the typical time scale of the system, decay and the oscillations, etc. Well, in an experiment, yes. In physics, yes. But in the simulation, analytically, I can do the limit mathematically and demonstrate that this is true. Yeah. Okay, I see what you mean. Yes, the error is polynomial. So in delta t, it appears as a prefactor in delta t. Yes. Yeah. Yes, because the gamma is encoded here. Lambda squared delta t is gamma, basically. So if the time scale of the change of gamma p is low compared to delta t, then I can do that.
Simply expand the exponential there.
Yes.
You collect the terms.
That's what I do. Second order in delta t, and that's how I do it. Yes, absolutely. Okay. Are we going okay? And I need to click again, sorry. Okay, and now, as I promised, no Markovian master equation, so we need some memory. There are many references about this, and I won't cite anyone so that I don't offend anyone. And one way to do this is the so-called reaction coordinate or Markovian embedding. And this is like this. So this is my original system, and this is yet another additional auxiliary environment that is coupled unitarily to the system and let's say permanently coupled to the system. So this is always like that, is always coupled. This new bipartite system is my enlarged system. And this auxiliary environment interacts with the collisions. So this is a Markovian environment that interacts with the auxiliary environment. But because the auxiliary environment is small, it has some memory. So if you think that this is a qubit and this is a qubit, my original system will interact with the system that has memory, because it's a small system, which is still interacting with the Markovian environment. So that's one way to create non-Markovianity, to create memory. The other way maybe is more efficient because it doesn't use another system, is to do the following. So we do the collisions as before, but when an ancilla interacts with the system and leaves, before leaving, it makes a small, like a partial swap with the next fresh one that is arriving. And so if you do it, for example, as a partial swap, incoherent partial swap, with some probability you swap it, with some probability you don't swap it. When you swap it, the system interacts again with the previous environment, and therefore this is a memory in the environment, if you want. This is probably easier if you have a limited resources. This doesn't use an additional environment. A very open question is, can we simulate any non-Markovian process? I don't know. These two methods reproduce some classes of non-Markovianity, but we don't know whether this exhausts all possible models. Okay, so now I'm going to thermodynamics a little bit. And so far we use thermal ancilla, so ancillas that are prepared in equilibrium state with a temperature. But what happens if we put some quantum coherence? And when I talk about quantum coherence, I'm talking about, sorry, and maybe this is also technical, I'm talking about coherence in the basis of energy eigenstates of the environment. Well, so this is, if you want, it's the Boltzmann state. Here we are adding an off-diagonal state, and we are doing this, sorry, delta t now becomes tau in this part of the talk, sorry. This is what happens when you do a Frankenstein of different presentations. And we do this with the square root of tau. That means that when tau goes to 0, when delta t, the collision time goes to 0, this coherence term goes to 0. So it's a very small coherence, but then eventually this leads to a modified master equation that contains a new bit in the commutator. So this is like an effective Hamiltonian that emerges because you have this coherent part. And this dissipative part is the usual Lindblad part. This G operator comes from the first order expectation value of the interaction between system and environment and the state of the ancilla. If you remember, when you do the derivation of master equations, normally in equilibrium, this first order term goes to 0 because the expectation value of the position X or P of the environment is 0. You always go to second order. This is the first order, basically. Okay, that's why it gives an effective renormalization of the Hamiltonian. But this has a lot of consequences. The first consequence is that when you do the energy balance of the system, so you want to look at the first law, you get two terms, okay? This term is the usual heat, is the incoherent heat. This is how if you open a textbook on open quantum systems like Petruccione, Breuer, for instance, that's the heat that you'll get. But then there is another term that we call it coherent work that comes from this renormalization of the Hamiltonian. So that's the first thing that happens. The first law is modified, but also the second law is modified. And we find that this coherent work is at least the change, the loss of coherence in the ancilla. The ancilla is coming with some initial coherence, with some off-diagonal elements. And when they do the collision, they lose some of this coherence, which is kind of transferred into the system. We show that this coherent work is at least this loss of coherence. So coherence, I'm not the first one to say it, is a resource in quantum thermodynamics and other quantum technologies. So we are going to see how we can exploit this coherence. So we got the new laws, but how do we exploit coherence? And I'm going to show you the thermal coherence, the thermal machine. So I'm going to say where thermodynamics come into play with this. So suppose I consider this setup. So I have the system. I have a cold bath, which is made of an ensemble of these ancillas prepared in thermal state at cold temperature T1. Hot bath is another set of qubits prepared in equilibrium at temperature T2. And then we do these collision models. So we bring the cold bus to interact with the system and then leave, and we bring the hot particles interact with the system and then leave. Then, as I'll show you in a moment, we can calculate the heat flux to and from the system, and also possibly the work that is created in the process. Why do we have heat? Because if you compute the energy balance of the environment before or after the collision, the energy difference will tell me the heat. So this is a very simple way of doing thermodynamics with this system. So heat, this incoherent heat, is just the energy difference of the ancilla before and after the collision. And okay, and this maybe I'll say it now. And the work is the work that you have to do to create these collisions. So these collisions, they come from a time-dependent Hamiltonian, because I had to switch on and off this interaction. And whenever you have a Hamiltonian that is time-dependent, there might be, in principle, be some work in the process. So this is the work, how I imagine the work done or injected into the system. Is the work done by the agent, could be the magnetic field or a laser that is producing the interaction between system and environment. Crucially, remember when I had this cartoon of the Caldera-Leggett model with the harmonic oscillator? In the Caldera-Leggett model, the system is permanently coupled to environment. So the work, if there is any, is only in the first moment that you build your system and you couple your system to environment. But then it's permanently coupled, there is no more work. Here, this is different because the environment is coupled and uncoupled and coupled and uncoupled every single time. And therefore, I have a work term every single time I couple a new ancilla to the system. So there is a work influx in this process that in the Caldera-Leggett I wouldn't have. In the Caldera-Leggett model, you have a system permanently coupled to one or more environments, and there is only heat exchange with the environment. There is no work. Okay. So based on this, I can have different modes of operations. One is called the oven or the accelerator. So this is when heat goes from the hot environment to the cold environment through the system. And this is accelerated by an influx of work into the system. And if you remember here, here I had two magnetic fields, two energy separation. B1 for the cold bus is the energy separation of this two-level system, and B2 the energy separation of the second level system. Depending on the ratio of these magnetic fields, I can have this oven or accelerator. The engine, which is, okay, heat goes into the normal hot to cold direction, and then some work is produced. This is when the ratio of the magnetic fields is between the ratio of the temperatures and 1. And the refrigerator, which is the case where heat goes in the opposite direction, the opposite natural, spontaneous direction. And this is done at the expense of some work that has to be introduced into the system. And this is when the ratio of the magnetic fields is smaller than the ratio of the temperatures. One can talk about efficiency, so I kind of mentioned it before. For the engine, this is the work produced divided by the heat from the hot bus. And this is given by this ratio here that only depends on the magnetic fields. And for the refrigerator, one can define a figure of merit, which is called the coefficient of performance. So this is how much heat you extract from the cold bus, from the coldest bus that you have in the refrigerator, and the work that you do to do that. So remember, in your fridge, the coldest bus is the interior of the refrigerator where you put your cold drinks, and then you want to know how much heat you extract from your cold drinks divided by how much energy in terms of electric power you put into your fridge. And again, this only depends on the ratio of the magnetic fields. These two values are the so-called Otto values because they are formally equivalent on the Otto engine that I talked before with the compression expansion. So formally it's the same thing. And they are strictly less than the Carnot value that only depends on the ratio of the temperatures because of these inequalities here. The Carnot limit is reached when the ratio of the temperatures is equal to the ratio of the magnetic fields. But at that stage, at that point, there is zero work and zero cooling. So W goes to 0 and Q goes to 0. And so the Carnot engine or refrigerator is, as you may remember, is the only reversible engine operating between two temperatures, T1 and T2, and for this reason is the most efficient. But because of what I said before, it has zero power. So it's a kind of useless device because, okay, it's the most efficient, but it doesn't produce you anything. You want to cool your drinks and you want to operate your car. So what people are maybe more interested in is the efficiency at maximum power. If you look at how the work changes when I change these magnetic fields, so suppose I fix the two temperatures, T1 and T2, and I change my device. Normally, if you do a diagram like this with work and efficiency, you get a curve. This is a sketch. You get a curve like this. So that's the trivial point where you don't do any compression expansion in the piston. And yes, so this is B1 equals to B2. And this is the Carnot point. The Carnot point is when the ratio of the magnetic fields is equal to the ratio of the temperatures. So these 2 points, they have zero work, trivially, okay? This one is the trivial point, this is the Carnot point. But then, okay, there must be a point in the middle where the efficiency is maximum. And we call this where the power is maximum. And we call this value the efficiency at maximum power. So what people are interested, not only in quantum thermodynamics, but even in classical thermodynamics, is the efficiency at maximum power, because that will tell you how efficient is your engine or refrigerator when you're operating at the maximum possible rate of production of work. And for a large class of system, the efficiency at maximum power is given by this value here, which is called the Coulson-Alborn value, which is kind of reminiscent of the Carnot limit. So it has the square root and only depends on the ratio of the temperatures. So it's kind of looks like it's universal, but it's not, in the sense that there are systems for which this is not true, okay? So if my system is a single qubit or a single harmonic oscillator, then the Coulson-Alborn can be proven. But if your system is 2 qubits or 2 oscillators and you have something more complicated, then you can violate Coulson-Alborn, you can go beyond Coulson-Alborn, okay? So it's not as fundamental as the Carnot limit. Okay, and so now we go back after this kind of parenthesis on thermodynamics. Now, how do we exploit coherence? So we go back to the case, and we consider this situation. So the situation is, again, 2 sets of ancillas, the cold ones and the hot ones. But now, in the cold baths, I'm going to put some coherence. And I want to see whether I get more work or more heat extraction than the thermal case. What we find analytically is that the efficiency of this process is still the auto efficiency, but we can surpass Carnot. Yes?
How different temperature in this conditional model of the ancillas?
So the state of the ancilla is a Boltzmann state. It's a Gibbs state.
For each one?
Each one is a Gibbs state.
So the path they made
yeah, they pass through an oven. They thermalized.
They thermalized, yeah. And then
let's say this is the ancilla. So that's the state of the ancilla. That's the typical. Now, in the case with the coherence, I'm going to put some extra term here of coherence. Okay. Right, so in this case, as I said, we still get the auto efficiency, but we can surpass Carnot. And this is, okay, so I'm not violating any thermodynamic law, so don't shout at me, but this is thanks to the input coherence. So I haven't, in the balance, I haven't put the work that is done to produce that state, okay? So I'm not cheating, but I'm wondering the following. Suppose that someone gives me coherence as a resource. How can I exploit it? This is my question, okay? So of course, if you start from first principles and you want to see how this coherence is produced and how much energy do I need to invest to produce this coherence, then the thermodynamic laws will be fulfilled and we will never be able to surpass Carnot. This is a situation where I'm already I already possess this coherence, and I want to see what happens if I can use it. Okay.
It's a bit misleading when you say the use of math. Of course, you have to get the work, the coherence.
Okay, fair enough. But is more, as you say, is misleading, but it's obvious that we cannot surpass Carnot. Okay, and Carnot is defined compared to this temperature. So remember that in this state we have the thermal state in equilibrium at temperature T plus an infinitesimal amount of coherence. This infinitesimal amount of coherence is able to make us do a lot of power at efficiencies even larger than what you would get in the Carnot with only this part. Okay, so you can take it in this point of view. But look, I even started from the beginning to say it, is a warning. This is thanks to the input coherence. It's more how we can use coherence to get more, okay, in this sense. Okay, any other angry complaint? No, I'm joking. Okay, and so these are the results. So that's the amount, this epsilon is the amount of coherence that I put in my ancillas. So if we concentrate on this epsilon equal to 0 first, we have 3 regimes. That's a refrigerator, engine, and accelerator of the oven, as we talked before, and the different transitions between them. This point is the Carnot point, again, separating the refrigerator and the engine. This is where the power will go to 0. So there are 2 things happening when we put epsilon. You can see that there is a new line bending like this. And so there is a crucial thing that happens, which is the fact that the refrigerator can kind of go over the region that without coherence would be an engine. So this looks an innocent thing, but it has a consequence, which is the fact that in this forbidden region, forbidden in the sense that classically you will have an engine. In this classically forbidden region, you have a refrigerator for which the coefficient of performance is larger than the Carnot value. Okay, so this is the case that you wouldn't have without coherence, and this is where we get the refrigerator. This is the first consequence. The second consequence is even maybe more dramatic, which is that we have also this new region appearing, which is called the hybrid refrigerator. The hybrid refrigerator is a device that is able to produce a heat current from the cold to the hot environment, and at the same time producing work. So it's the opposite of a refrigerator, because it does both. It's both an engine and a refrigerator. So, and again, this is because when we are injecting coherent particles in the cold bath, we are injecting some extra source of work, which is making these things possible at the same time. Okay, it's not an equilibrium bath; it's a bath endowed with special resources. Okay. Okay, so that's when we put coherence in the cold baths. When we put coherence in the hot baths, situation is similar. Again, with no coherence, we get the 3 regimes: refrigerator, engine, accelerator. When we put coherence, so epsilon is larger than 0. Again, we see that there is the engine that, the engine that goes into this classically forbidden regime. And in this case, the efficiency of the engine is larger than the Carnot value. There is no hybrid refrigerator here. And we have a conjecture why this is, because this is coherence in the hot bath. And for this reason, it's not creating, it's kind of introducing coherence in the wrong bath, if you want, for doing the refrigeration. And then we looked at the efficiency at maximum power. So we looked at how the power changes depending on the efficiency, or if you want, this is parametric plot between the 2 quantities. So when epsilon equal to 0, we have the sketch that's similar to a sketch that I showed you before. So this is the efficiency at maximum power. This is the Kurzon-Albor limit, and this is the Carnot limit. And when you put some coherence, even not very large, 2 things happen. The first one is that the efficiency at maximum power is larger than the Kurzon-Albor limit, thanks to coherence. And the second thing is that there is a whole region of points for which the engine surpasses the Carnot value. We can define an effective Carnot bound. And if you want this, yes, this addresses Luigi's point. The effective Carnot bound takes into account the fact that I'm introducing resources in the ancilla, and we can never surpass this effective Carnot bound. So this is the fair comparison that one would have. Okay. Okay, actually I go perfectly in time. So that's the summary of this first part. So I've told you how collision models allow the simulations of consistent thermodynamic processes of open quantum systems. The thermodynamic approach is shown in this paper here. I'll show you how to simulate efficiently any Markovian Liebland master equation. And I've told you how you can enhance quantum machines with coherence. And I haven't told you how you can use also entangled ancillas to interact with the system so that they interact with correlated bus. Good, so let me skip to the acknowledgements. So I don't have time to talk about the second part, but if you are interested, I'm gonna be here until Wednesday. So if you want to talk about quantum annealing, I'll be happy to chat about this. Sorry. Sorry. Good. Thanks. And these are my collaborators. Thank you very much for your attention.
Thank you very much, Gabriele, for the nice talk, and congratulations on the results. We had several questions already, but we have a couple more minutes. So, I mean, in the curves in the curves you've shown, there was the first line bending to the right or to the left. This was the Carnot bound. And the second bound, why doesn't this happen there? It's of course not well defined, maybe.
Let me see. Sorry, but is there a way I can go there? Maybe I can go there. No, wait. Probably I manage. This. Is this the plot? No.
No. Yes, this.
In this one, and what is the question again?
The limit between the accelerating and the end.
Yes.
This is not defined by the Carnot limit.
No. This is the trivial point where I don't do a compression expansion. This is the stupid point, right? So this is when in the if you want, in the picture of compressing compression and expansion, this is when the compression expansion don't happen because the frequencies are equal. If I then go beyond this, which means that I expand instead of compress and I compress instead of expand, you get the accelerator, which is the stupid, well, not stupid, is the regime in which heat goes in the normal direction and you accelerate the heat current by putting work into it. Okay. Good. Thank you.
Previous plots are fine.
Yeah.
I'm not clear. This is a theoretical system.
Yes.
Is there any evidence of any experiment proving these traits?
Unfortunately not. So we were working on it. No, I shouldn't tell the gossip. No, there's no experiment, but we believe this can be done reasonably easily with with superconducting qubits. In this, I know that you are working in this institute. You're also working on superconducting qubits. But let's say that with commercial cloud quantum computers, this can be done quite easily, I think.
Can be done what?
Okay, it can be done easily. Okay, because there is an experiment there is a demonstration on cloud quantum computers of this line here of epsilon equal to 0. So this has been demonstrated with collision models on IBM quantum computers. Simulated or demonstrated or?
No, I really would like to prove things, really.
Yes.
Then we have a different idea. What is a simulation?
Okay, so I repeat, it's a demonstration on cloud computers, on cloud quantum computers. If you want to call it that an experiment, we can have a discussion, okay? I'm not so convinced. It's a different kind of experiment because it's a simulation. The people doing the simulations are not in the lab manufacturing the chips and controlling the circuits. What I'm saying is that there's been an experiment with collision models on superconducting qubits, a simulation on superconducting qubits at no coherence, okay? And these regimes have been demonstrated. Now, to change the state of the ancilla from a diagonal state to a non-diagonal state, I don't think is a complicated thing, given the technology that they have. So it would be straightforward to also consider epsilon larger than 0 in this diagram. This is what I'm saying.
Any other question?
Can you comment more on that? So, okay, can you remind me how to implement the scheme epsilon to 0? But how do you implement the collisional model in with the superconducting?
It's CNOT gates at the end of the day.
Make a sequence of CNOT
gates
on.
Yes, it's single qubit.
Yeah, it's a transparency we discussed.
Okay, and then how you make the coherence? Okay, you change
in the preparation, it's the preparation of the ancillas. And the preparation of the ancilla is single qubit gates. So you start from 0, for instance, and then you start building your this.
Okay.
There is a caveat there, okay, which is very hard in this kind of quantum computers to create mixed states. Okay, this is a caveat. So what people can do in reality is to do the square root of this state and do a pure state that when you do the density matrix looks similar to that, okay? And when you trace out, in many properties, there is no difference, but fundamentally there is a difference between the two things, okay? So some people modify this into a pure state.
So, I mean, you can also do it randomizing the state without
exactly
extra ancilla.
But then you need to repeat this. If you have many ancillas, you have to repeat
but you
all
will
the
need
ensemble.
to repeat anyway to get statistics.
Yeah, there is a trade-off between all these things. Absolutely.
Okay. Sorry?
If it is a single qubit, you end up only playing with the population.
Exactly, in the basis of the Hamiltonian of a single qubit. So yeah, you can do.
You can also do a pair. You can also do these entangled with another one and ignore one. But of course, these are resources that you don't want to lose. So.
All right. Any other question? What you want to ask them? No, Lisa. Don't you have any question? All right, then if not, we thank the speaker again.
Thank you.
For a nice talk.
Thanks a lot.